Welcome you all to the Spark Research YouTube channel. This is Dr. Virchandra, Assistant Professor in the Department of ECE, and here is the another session for this particular series, your electronics devices. And in this session, we are going to take the contents from your PCB design, and particularly we are going to take the contents from the unit second, right? So we will look into the introduction to the power electronics. Before going ahead, let me tell you, gate isn't cracked in the final year. It's built quietly from the very first lecture, one concept at a time. So stay consistent and your future self will thank you. So you can start to prepare from day first. So here is the syllabus for your unit second, introduction to the power electronics. We will look into them, and then introduction to the semiconductor power devices, and we'll look the some special type of the semiconductor devices which is being used for power electronics like diodes, and then we'll look into the thyristors, PNP type of the structures, and then some switching characteristic of the BJT and MOSFETs, and finally the sub fabrication steps. Okay, so let's go into the details now. So for question number one is this, what is this power electronics? So whenever we are talking about this power electronics means we are going to deal with the higher power, means higher voltage and higher current, right? So that is why we are calling it as a power electronics. So here, like the some examples, you may see the diodes, the MOSFETs, the IGFET, all these components can be used for the power devices, power electronics purposes. Some more applications, if we look into them, then we can use it in the industry applications, some renewable energy, transportation. Why is it being used? So energy, the efficient energy conversion purpose, then control of electrical power purpose, industry, and the renewable integration. So we are using it for multiple applications in our daily life as well. So let's talk about it, that what are these power electronics. So here is the introduction. So power electronics is a branch of electrical engineering that deals with the conversion, control, and conditioning of electrical power, right? Using your electronics device. So how will you convert your, the electrical in your power, like you are talking about the 33,000 volts, or maybe the domestic voltage, maybe 220 volts. So how will you convert exactly? So in these cases, you need the diodes or the MOSFETs and IGBTs. So all these combinedly will, the parts of the power electronics. So major thing is the conversion and control, right? So they, the major areas, your power, so handling high voltage or high current, so that is power is equal to nothing. Power is your voltage and current. So if it is both are high, of course the power will be high, right? Then electronics, solid state device which is being used to control, then control systems, so regulated power output. So these are the main, the main objective is efficiently conversion electrical energy from one to another, so that loss should be lesser, right? So that is the main objective. So some major applications like your motor drives, then the welding equipments, induction heating, then power system. You can see the renewable energy purposes, then wind energy conversion, and all these, right? Transportation, your electrical vehicles. Nowadays we are using UPS system. And what are the major roles of the power electronics? So major role is in the energy conversion. Efficiently energy conversion means whenever we are converging the power, the loss factor must be very less, so that we can transfer the energy from one to another very easily. Then control of the electrical power. So these are the important, like why the power electronics are important, because we want to control over these energy saving. So this is another reason. Then integration of renewable energy into a same package like solar, wind, so that we can useful, right? So these are the roles. Now, so introduction to this power semiconductor devices now. So mostly we are going to use this power diode, then power thyristor, then power MOSFET, and then power IGBT. So these are the major, the power semiconductor devices. Why are we using this power diode? Because normal diode like 4001 is using for only electronic purpose, but that is not can be used for electric purpose, right? So means so high power, in that case it will not be used. So power diode will be used here. So the idea is that it will allows the currents in a one direction, but not the in milliampere. Here the amount of current may be in the ampere, so high current converts AC to DC. Of course, the working principle is almost same like your normal diode, but major thing is that that will deals with the higher current, higher voltage. Simple and robust. Similarly, thyristors, so control rectifier, it is being used to blocks and the conducts high currents, and used in AC DC switching also. MOSFET again the same working principle. Voltage control switch is there, a fast switching speed, so used in the SMPS and the inverters. So why? What is the difference? So only one difference, that all these semiconductors devices are dealing with the high power or high current and voltage. So power semiconductor controls and switch high electrical powers, enabling energy conversion and regulation in modern electrical system. So power semiconductor device is electronic components designed to handle the control high voltage and high current in power electronic circuit. Right. So this is the major difference. Like in normally what is happening, the small signal device they build for power conversion, switching and the control application. So why power device? So of course the large current, large voltage. So power is equal to V into I. And the another purpose is that it should always have the less low power loss. Thermal stress it can hold on, means the more temperature, right? Then the types of the power semiconductor devices, your uncontrolled devices, your maybe the power diodes, so used for rectification purpose. Semi-controlled devices, your thyristors, or turn on by gate, like there is a gate terminal, so you can turn on and then turn off naturally also, right? Fully controlled like VGT, MOSFET, IGT, these are, these can be turned on and off using the control signals, especially the gate terminal. So you can turn on and off. Applications AC-DC conversion, particularly DC to DC or DC to AC, also motor drivers, inverters, UPS, so multiple applications. We have already gone through that. Okay. So now we look individual one. So power diode. So already we got the introduction. So power diode or a high power diode is one of the power semiconductor devices that have two terminals, right? As usual, cathode and anode. So it will be very similar to the PN normal junction diode. There is not a difference. Only difference is here doping. The doping concentration is how much? Doping of P type of material is 10 to the power 19. So very, very, very high doping, right? And the dimensions is also large. Not only doping dimensions, of course it will require the large dimensions, right? So 10 mm, right? And here also see the doping of the n layer. So again very high, 10 to the power 14, and n plus layer, so 10 to the power 19. So doping is very, very high, and width is see here 250 to 300 millimeter. So very high dimension. So that is why this is the power diode. Symbol is simple, the similar to your normal diode only, and characteristic will be also like the as like normal diode, right? So here is the symbol, like not symbol, just the real. And the characteristic is the in the forward direction your current will flow, and in the reverse bias direction no current, but after the breakdown, right? After the breakdown only, like the some amount of current definitely it will flow. So similar to the normal diode. The special cases, some more diodes that are being used for the power diode case only. So gun diode is considered as a type of the diode even though it does not contain a typical PN junction, right? So still this is called the gun diode. So here if you see the structure of this gun diode, N plus layer is there, N is there and N plus. So if we look into the structure, then it contains the only N type of material, right? So N type of semiconductor, it consists only of N type of semiconductor material, that is majority carriers will be electron. So it generate the short radio waves such as microwave. It utilizes the gun effect, right? So its characteristic, you can see initially the amount of current will flow, and once the number of majority carriers will reach to the saturation level, further the holes will be accumulated at the end. So now because of the accumulation, now what will happen, the amount of the current will decrease here, and it will keep on decreasing. After reaching to the valley points, again the amount of current will keep on increasing as like normal diode. So these regions will act like normal diode. Before that there is a changes, right? So this is the special case for the gun diode. Okay, so here you can see the characteristics. So in this region negative resistance is there, right? Negative resistance means your current is decreasing. Before, like in this region current is increasing, in this region also current is increasing. Okay, so the here gun effect, you can check the the in between peak to valley, the gun effect is there, that at low electric field electron occupy the valley. So because of this, that is why this is called the the gun diode also. So when the electric field exceed the electric the critical value, the electronic transfer to the L valley causes a sudden increase on the velocity. So this leads to the formation of high velocity electron domains, producing negative resistance. Okay, so let's take some more diodes. So Schottky diode, this is also one type of the diode, known as the hot carrier diode also sometime, right? So low voltage diode also, or the Schottky barrier diode. So this is actually made by only metal and the N type of silicon. So again, there is no P type of material, only N and the N type, the metal type. Metal means your copper, aluminum, Ne, right? So we know that in PN junction diode, P-type and N-type semiconductors are joined, but here, in Schottky design, you have to use only metal. But if you look into the symbol, like similar to the normal diode, only use this type of the symbol, and characteristic will be almost same, right? So in the forward bias, the current will keep on decreasing. Here, cut-in voltage will be very low. So this is the difference. And in the reverse bias, again, the almost there is no current in this region. But again, if we keep on applying the higher reverse bias voltage, in that case, it will be the high amount. So after breakdown only. Impact diode, so again here you can see the structure, so PNIN. So this is the P doped region, so normal, the N type of region. Intrinsic, I stands for intrinsic, means no N doped, no P doped, completely pure silicon region. N plus, here your arsenic is the doped. Okay, not phosphorus is the phosphorus or arsenic is stopped. Again, the that is basically used as an oscillator and amplifier at microwave frequencies. The operating range of impact diode may lies in the 3 to 100 gigahertz. And characteristic of your impact diode is very similar to the gun diode, only it will have the negative resistance, and again it will have the similar characteristic, right? Like to the diode. So it will follow almost similar type of characteristic. Then thyristor. Next to these are the major types of the diodes that we have discussed. Thyristor means we are now going to talk about the four layer type of the semiconductor devices. Particularly we'll have the pattern of PN type of the devices, right? So it is also called as the controlled electrode. The most common type of your thyristor is called SCR, silicon controlled rectifier. So, despite being physically a small devices, thyristor can control high voltage and the levels of current. So, are used in the high voltage direct current power transmission line. Why is it being used here? Power switches in the factories, then vehicle ignition switches, control the speed of the electric motors, then liquid level regulators. So these are the major applications. Some examples, so PNPN, that is also called the circular devices. So this is the example of your, the thyristor, and again it will have the definitely the four layers, that is PNPN, and the function is normal diode without any triggering inputs. So only difference is the triggering, and that is the gate. And in reverse bias, no condition, no current flow through it. In forward bias, the conditions flows through it, and the voltage across it is more the breakover voltage of it, right? And similarly, since if you will check the working principle, then it will have the PNPN structure. So there are one junction, two junction, and the total how many junctions? Three junctions. You can also the equivalently you can the replace by 2 BZT, that is PNPN and then NPN, right? So PNP and NPN, so two transistors, so equivalently you can draw like that. Symbol for the circular diode is this. You can use it for your exam purposes. Now working principle. So initially what will happen, like initially if you are standing at 0, now suppose the forward voltage if you are increasing, then initially what will happen, amount of current will flow very less, very less, very less, very less, very less. Now suddenly what will happen, after reaching to this VBO voltage, now amount of current will be very in, they keep on increasing. Even if you will decrease the VBO voltage, still your amount of current is increasing, right? See, keep on increasing. And further, at this level, this is called the latching current, right? So at this level, whatever is required, the VBO, if you are increasing, then ultimately it will turn on. So after turn on, the amount of current will be the will be very high. So the minimum current that requires to make it turn on your devices, that is called holding current. And latching current is the minimum current that requires at this level, that is VBO, in order to make it forward. So that is your latching current. So both are different. Now once you will turn on your devices, then these regions will not come automatically turn on. The current will start from this, and turn off means 0, right? In break, if after from the apart from the beat, the breakdown region. So normally you will have these type of current patterns in the thyristors in switch on condition, and these things are valid for only first time. So this is the working principle. And now how is it happening here? So once the PNPN devices is there, so number of holes, number of electrons are there. So once the number of holes will exceed, automatically it will start to flow through the region, right? And once it will start through the region, and automatically whatever the gate voltage, here the gate voltage is there. So the maintaining the gate voltage, you can control the flow of current in the thyristor. Okay, so silicon controlled rectifier, or the semiconductor controlled rectifier is a four layer, exactly the same that we have discussed in the previous one. So this makes them applicable in medium and high AC power. The operations such as motor function, right? Here only the difference is that we are using the gate terminal here, and the structure is same like PNPN devices, and the here we are using the another one voltage in silicon controlled rectifier. So by the controlling this voltage, now you can the easily turn on and turn off your thyristor. So the working principle of your device will be similar to your PNPN structure only. So gate will trigger, and once the trigger done only, it will on, and so this will follow this pattern, right? Okay, so this is only for after first time only. If it is you are triggering the first time, then you have to go to the this much of VBO, right? That is called the knee or breakdown voltage. So these are the your forward or on condition, and this is of course in the off condition. The working principle, we have whatever we have discussed in the previous slide, that will be valid here. So physics of your now switching characteristic, now we are going to look into that. So PNP, that is NPN, this is a transistor, the representation is here, and this is the fixed bias conditions. Here you can see this is a BZT, then RC, and then IE. So, and you are going to connect your supply like inputs at the base terminal. So here you are going to give the inputs, and here we are going to collect the output, right? So the RC term input, this is your input characteristic, and here is the output characteristic. That is how the output characteristic means whatever the current you are receiving at this terminal, that is IC. So IC versus BCE. And input characteristic means how much input current you are giving here at this IB terminal. So what will be the IB corresponding to the VBE, this one, right? So that is the input characteristic. Okay, so here you can find out the IV and the amount of the IV and IC using the one-line equations in your the fixed bias condition. If you can look into that, right? So one two equations, just IC and IV. How will you find? So the IB is the difference of VB minus VB divided by RB, and IC is nothing, VCC minus VCE divided by R of C, right? And so once it will be 0, like IC is equal to 0, that will case the VCC. You can check it how much. Okay, so characteristic, like here whatever the inputs you are giving across the VV, you can check the how much voltage that will reflect across the VBE, and correspondingly output we are going to observe of course at the collector terminal. So that is the VCE. So of course it will have the some time delay. So corresponding here you are giving the 1, so you will get the 0 and 0 then 1. So just the whatever the voltage you are giving, since this is have the phase shift of 180, right? So this is the major crux, the switching characteristic, like that you can draw. Of course the time delay that the inputs you are giving, and that exactly the time you requires to get the output, so that is called the on time. And similarly off time is just that requires to turn off or from getting the 1 to 0. So MOSFET characteristic, again the similar to that only. This is the the structure. If you remember, this is the N type material, P type of substrate is there, channel in between them and layer, and then there is a silicon dioxide layer. This is, and diffusion by diffusion you can grow this N layer and N layer. So you can also have the also the gate terminal, and next to the gate terminal you will have also the one voltage, that is gate voltage, and this is your VDD. And the input and output characteristic you can check. So this is your output characteristic across the VDS versus the I of D, right? So how whatever the amount of current is flowing through this and the voltage that you are applying, so that is your output characteristic. Here is your switching characteristic. So whenever you are applying the input voltage corresponding to that, you are able to observe the output. So that is your switching characteristic. Now we'll look into the some fabrication. So IC fabrication. So here you can see the small scale integration, medium scale integration. So we are moving through the VLSI. So that is one of the important. What is this integration? So we exactly wanted to integrate the multiple huge numbers of the components, the electronics components on a same package. So that is called the the scaling. So that is why we are talking about the some special fabrication technology, so that we can integrate the thousands or millions of the components on a same IC, same package, right? So a monolithic integration is that one. So all circuits components, both active passive elements and their interconnection, and manufacture into a single silicon chip. So this is the crux of the monolithic integration. And what are that? So here PN junction isolation and the unipolar is your MOSFETs. These are the devices, right? So that is called the monolithic. What is the monolithic? So integrating the multiple components on a same chip. Steps: prepare the silicon wafer, then oxidation, second steps in order to develop this SiO2 layer, photolithography. So here use the photoresist to develop the photolithography. So this is nothing, this is to develop the multiple layers over this, the SiO2 layer. So you can develop as per your requirements. Further, if you have grown some extra layer, you can etch or erase. So that is called the etching. Doping is that if you wanted to dope the some layer inside the your the SiO2, so that is called doping. So by diffusion technique you can dope. Then after doping you can the do the routing. So metallization, that is provide the contact among all the layers, finally packaging. So these are the major steps of the fabrication. Right? So we have discussed in short. Here you can check this all the steps. Silicon wafer preparation that will provide the mechanical support, and also you can have the the maintain the clean, then epitaxial layer which will grow the 100% pure silicon, the not only silicon or whatever the you required one, right? Then oxidation develop the SiO2 which insulates the protect the layer. Also photolithography using the UV light you can do it in order to grow the layers. Etching you can remove the unwanted layers that you have grown. Diffusion you can grow the N layer, P layer, right? Metallization you can provide the contact. Passivation so protect layer added the prevent contamination. Testing you can test advantage high reliability and compact size, and the speed will be very high. Now we look into the fabrication of the monolithic diode. So here like the same process we are going to follow. First have the substrate preparation, then you can have the diffusion process, then you can now the go for the this is the oxidation process, diffusion process, and then photolithography. Here only we are following, right? So using the photolithography, you can open the window here, and then you can grow the layers, whatever exactly you want, and then PNP like that you can device you can create. Lastly, here we are providing the contact, that is the metallization. So this is the how we'll do the for monolithic diode. Similarly, you can develop the capacitors. So again, same process, substrate preparation, oxidation is there, and then P impurities are developing using the diffusion technique, right? So P substrate is there, and over that you are the creating one layer that will be causing the the layers, that will cause the two different layers, and finally you can provide the contact. So this is SiO2 layer only, and here if you're providing the contact, so it will becomes almost two plates, that is the causing of the one capacitor. So resistance is equal to rho L by A, so that is how you can develop the monolithic resistance, right? Okay, that's all in this session. And so lastly, before going concluding the session, let me tell you, play today, stay healthy tomorrow, and learn for a lifetime. Thank you.